So, hello everybody. I'm Leonardo Linguaglossa. I'm a postdoctoral researcher at Telecom ParisTech, and I will talk about my ongoing work that I am carrying here at Links. So, many of you already know me because I spent the last 6 years of my life here at Links. And funny story, I changed 3 affiliations because I was at first with Bell Labs, then INRI, and now Telecom ParisTech. And I obtained 2 academical titles, first the Master of Science and then the PhD. But I never changed my desk, which is always the same here at Links. Yeah, so it's a reverse mobility, it's stability. I mean, only the... But many things change because since the beginning I've been working on many subjects, so I'm not going to go into the details of everything that I've done, but I spend most of my time doing something in between applied research and theoretical research with some new entries such as machine learning, because now everybody has to do this, so I put it here. But that's not the topic today. So today I will just focus on high-speed networks. In particular, my research is mostly focused on software routers and network function virtualization. And I will show why modeling of this kind of networks and this kind of behaviors is very difficult. So we all know that at the beginning the internet was not what we observe today, because everything was constrained. The topologies were coupled with the geography, the geographical locations of the routers. The functionalities was coupled with the size of devices, so more functionalities means bigger sizes. And in general, everything that is related to maintenance was coupled with the human interactions. But now everything is going to change. We have virtualization techniques, which allows us to get rid of the problems of the physical locations of devices. The size of a device is not really a problem right now. So miniaturization of devices with the same functionalities, and we are further reducing the human intervention. But so this is not everything is gold, because in fact what we observed is that we have many different research directions with contrasting requirements, and more often those requirements are really one against each other. So we plan on having a network softwareization, but software is much slower than the equivalent hardware solutions, and so this is a contrast. We are planning on having everything on cloud, but yes, we also tend to have decentralized techniques. We deal with non-homogeneous technology, and each technology has its own constraint and its own problematics. So what we observed is that somehow the paradigm of network function virtualization, so the fact of replacing hardware middle boxes with the equivalent sequence of code, takes at once all the challenges. In fact, this is an example of a network with many middle boxes. We have firewall that are doing a certain kind of processing, but we also have caches, different kind of processing. We have log systems. Here it's not shown, but we can have 5G gateways for the network, for the access network. So somehow what we observed is that the solution provided by software network as an enabler of NFV is a key point on the network softwareization. So after this preamble, I will show you the outline of the talk. So at first I will discuss about the software routers. I will talk about why accelerating software routers is important and difficult. And then I will focus on the performance modeling of such devices. I will show some measurements that we took on real equipment, and I will introduce our discrete-time model for evaluating the performance of an NFV router. I also give credits to my collaborators. In particular, I worked with Dario Rossi and Salvatore Pontarelli. They were at the moment here at Links, so I noted this as collaborators, but I also collaborated with people from Germany, in particular from the University of Würzburg and TU Berlin. And the results that I am going to show you today are or have been presented in previous conferences, in particular at Infocom and at SIGCOM for the demos and for the model. And there are some ongoing work for the extensions for a journal. So now let's start with part one. I'm on schedule, and so that's very good. Some background on software routers. So the softwareization of networking is based on a trade-off between the functionality and the speed of the hardware black boxes and the flexibility of the equivalent software component. So what we have here is that we want to get rid of the hardware black boxes, and we want to use a general purpose hardware to build, on top of which we can build our network application. So in the last decade, there have been a lot of effort in identifying what are the components of this of such an architecture, and on deciding which part can be accelerated, and at which point we can enable some faster packet processing at this level. So here I put on perspective the equivalent hardware with the software model that is shown at the right part of this picture, and I will show you a little bit the history on the software acceleration technique. In fact, one of the first programs that has been developed to put the networking functionalities on software is the click modular router, dating 1999. And you can see that at that point, they thought it could be more interesting to put the high-speed part of the processing as close as possible to the hardware. In fact, here on the right side, you see that there is a first separation between hardware and software, but even within software, we have a further separation. That is, we have the kernel space and the user space. So the click modular router was developed in kernel space. That was not a good idea, because the kernel is much slower than, and it cannot deal with the growing requirements of high-speed packet processing. And in fact, one of the latest approaches, that is the DPDK, is implementing a complete kernel bypass. So rather than moving the high-speed functionalities, rather than placing the high-speed functionalities close to the hardware, we abstract some of the complexity from the hardware, and we brought APIs directly on top of the user space. So in order to do so, there has been a lot of research for producing what we call the software acceleration techniques. Now, there are many of them. I will focus just on a few of them to show you how it works. And then I will show how we end up with what we call software routers. One of the examples of a software router is the vector packet processor. That is an open source implementation of high-end Cisco routers programming model. In fact, what I mean is that this exact code was at first built inside the high-speed Cisco routers, and it has now been released open source, so we can access the code and we can work on it. But this is just an example, and pretty much every other frameworks work the same. What you can see here is that the VPP, the vector packet processor, also abbreviated in VPP, is decoupling the network functionalities in what we call nodes. Each node is implementing only a subset of the functionalities. I highlighted the Ethernet-related nodes and the IP-related nodes in the figures. All those nodes are linked and connected to each other to form what is called a processing graph. And the processing graph represents the packet processing that needs to be performed on the incoming packets. So we typically have division within the nodes, and we have also libraries to perform the graph traversal, that is the packet processing. And we can even extend with custom plugins. Now, why software routers have an important role in NFV? Because they can enable what is achieved nowadays in NFV networks. So there are many different possibilities on how to implement NFV. One of these possibilities is to use an SRIOV model, that is NICs, so network interface cards, are built with an internal switch that can be used to connect different applications, and each application is a virtual network function. But this is still a hardware solution, because it's we are using the resources provided by the NIC. Then here is where the software routers have a role, because two other alternatives is either to use a standalone application, so use a simple framework such as VPP and create on top of it our network functions, or we can, in a simpler manner, use the software router, as in the case 3, just to link virtual machines or containers. This can be implemented in many different things, so that all the development part is transparent to us. We just use the software router as we could use a regular router to connect devices, so to connect middle boxes in this case. So now, I talked a little bit about acceleration techniques. I will show here a sequence of what are the most important acceleration techniques for software routers. Our first technique is what is called the flow awareness, in the sense that NICs provides already a mechanism to understand the different flows that are arriving at the network level. This is done using hardware queues, and each flow is identified by the 5th tuple. So the typical IP source, IP destination, MAC source, MAC destination, the IP protocol. And this is done directly at the hardware level, but it is exposed at software level. This means that we can deal with the high level of parallelism, because we can assign each hardware queue to a different core, thus allowing multi-core scalability. Another technique is the zero-copy technique, because this is very important, because it reduces the memory accesses that are performed at the software level. And the idea behind this technique is that we typically don't deal with all the operations on the whole payload of a packet. We normally just access some metadata, such as the MAC source destination or the IP source destination. So the zero-copy techniques allows us to store the packet in a separate buffer and to provide an API to the software that is a copy of only the mostly used of the often used data fields, such as the MAC address and the IP source address. Then one of the most important techniques that is used for software packet processing is the batching. Now, batching is very important, because it will be one of the complexities that we dealt with in our model. And in particular, here I show that how it works. We have a set of packets arriving at the interfaces. at the NIC interface, but the software router is not dealing with each individual arrivals. It is dealing with a group of packets. So the packets are batched in a separate buffer, then they are grabbed at once. All the processing occurs at once as well, hence the batching processing, and even the departures are batched. This is very important because batching can maximize the utilization of the CPU pipelines, and we will see it later. Then there are some other techniques that are mostly related to the memory allocation of the underlying operating system, such as the huge pages and mempools. In Linux, typically we have our RAM, our memory, that is divided in multiple pages of the dimension of 4 kilobytes. But then what happens when we run out of memory in one of these pages? It occurs a page fault, and then the page should be replaced with another portion of memory. We can just allocate a huge page, hence the name huge pages, to limit the page fault. And we can even make use of mempools and the pre-allocation of a bunch of this memory to avoid runtime allocation of memory. Now, I was talking about the CPUs, because nowadays CPU are implemented with, are realized with a set of pipelines. Each pipeline, each element of the pipeline is a stage in the instruction processing. We have instruction fetch, instruction decode, and then we can have one or multiple ALUs that are the components that are performing exactly the computation. But pipelines are much more complex than this. We can have up to 20 stages, and we can have multiple ALUs, multiple components that are performing the computation. So the idea is to give hints to the compiler in order to maximize the utilization of of such an architecture. For instance, we can explicitly write our packet processing to deal with packets in groups of 2 or 4, so that we can maximize the so-called instructions per clock cycles, because in one single clock cycles we can issue more than one instruction. And we can even do something more funny, so like predicting branches and predict what is the most likely condition that is going to occur, to give hints to the compiler so that the pipeline is always full and it is always used at its maximum potential. Now, this is only a subset of all the possible acceleration techniques. There are many that I cannot detail right now. So if you're interested, I am a co-author of a survey of all the performance acceleration techniques that is appearing in 2019 at the proceedings of IEEE. So, takeaway of this part is that this is an example of a simple NFV router. So we have multiple components, all the multiple processing occurring at the same time. And so our challenge is to have a precise model of this of such an architecture. And this is what I am going to present right now in this second part of the talk. So I'm sorry. So first of all, I will discuss about some measurements that we took in our experimental testbed here at Telecom ParisTech. And then I will focus on the modeling of exactly this scenario. So, first of all, we consider a device under test, that is our software router. The software router that we chose is the FDIO router. In this router, we are implementing a set of virtual network functions. We chose Ethernet, simple Ethernet, simple L2 switching. We chose IPv4, IPv6, or even a mixture of this kind of processing. And the software router is bound to a CPU. a single core that is performing all the batch processing. Now, we will produce an input rate from a traffic generator. This input rate this traffic will reach the, the device under test, but not all traffic will traverse. Not all traffic will traverse the router because some traffic will be dropped due to the bottleneck created by the CPU. Then we will measure the forwarding rate at the output of the device under test, and we will also measure some other parameters, some other variables such as the latency. So we use the two line cards, two 10 gigabit per second line cards, each one connected as shown in the picture. And we create all the experimental testbed, all the dataset, and everything is publicly available at GitHub. So, why is this important? First of all, because we discussed about the batching. But batching has a limit. In particular, we can batch packets up to a maximum batch size, which depends on the input load. And this is what is shown in this graph. So, as a function of the normalized input load, which goes from 0 gigabit per second to 1 times 10 gigabit per second, we measure what are the batch sizes that are observed inside the device. And we show a funny thing. So there is a low speed mode at which that arrives up to 85%, 82% of the maximum forwarding rate, in which the batches observed are very small, typically less than 50. Then this evolves until when we reach the so-called high-speed mode, where many things are happening at the same time. So there is not a single mode, there are many modes. This scatter plot is becoming more sparse. But we observe that on average we are just privileging the maximum batch size. And why is this important? Because in this plot I show you the number of instructions per packet as a function of the maximum batch size, of the maximum vector size. And we observe that for three kinds of processing, for the simple L2 forwarding, for the IP forwarding, and for a mixed scenario, having small batches implies a huge penalty, because here, when batches are small, the number of instructions per packet is much higher. Then, as soon as the batches become bigger and bigger, there is we are dealing with the penalty. With the penalty due to the software framework. In fact, we are amortizing the framework cost up to a limit that is the limit of the framework. In this particular case, for the simple L2 scenario, the cross-connect scenario, we require at least 500 instructions for each packet. So then, of course, batching introduces some latency. And here I am plotting the latency measured in microseconds for the three scenarios, for the cross-connect, for the IP scenario, and for a mixed scenario in which we have a mixture of traffic. And we observe what happens when we measure the latency at 10% of the maximum forwarding rate, at 50% of the maximum forwarding rate, and at 99% of the maximum forwarding rate. So for low rate, the instructions per packet, we observed it was much higher, but the latency was much lower. And in fact, this holds true across all the network functions that we observed. Then, when we start approaching the maximum forwarding rate, the latency becomes higher and with a higher variance. Because big batches imply that any packet at the batch will observe a different latency depending on the position at which it was found within the single batch. So how do we model such a scenario? We we decided to go for a very simple model. So we just consider a queue of capacity L. The capacity L is the maximum queue size that is admitted, that is allowed at the NIC, so at the network interface card. And those packets in this queue of capacity L will be accessed by a processing module. So our server is just the batch processing that is busy polling, so it continuously polls packet from the queue, and it picks up packets in a range that goes from 0 to beta, which is our maximum batch size. Now, this is true also for our experimental evaluation. In fact, when no traffic is injected in our software router, the CPU continuously polls the interface, providing does batches of 0 packets. So internally, the software router is implemented such that even when there is no traffic within the network interface card, the batch processing cannot be deactivated, and it's always polling for more packets. Now, another assumption that we had is that we are considering a FIFO queue, first in, first out. While in typical software routers, we are not dealing with queues, we are dealing with packet rings. So it means that in case of an overflow of this queue, for a FIFO queue, the most recent packets will be dropped. But for a ring queue, the oldest packets will be dropped because a circular queue will start back from the beginning. But the nice thing is that we don't care about which packets are dropped. We are only interested in how many packets are dropped. And this assumption is sufficient for that purpose. Also, we are completely ignoring all the complexity of an NFV router. So we are just considering the batching. In particular, before I showed you that we can have batching at multiple levels. We have the batching at the input and the batching during the processing and the batching at the output. But in this case, we just ignore all the complexity. So all the scenario that we observed in the previous slides can be reduced in this scenario. Then we introduce two elements, so arrival process of packets. Each arrival will increment the queue by 1. And we have the polling process of service time bi, because each polling will reduce the size of the queue by I, that is the batch that is grabbed. And the interesting part here is that the service time is not constant, because the service time depends on the batch size, as we observed in the previous plot. So big batches will have a better efficiency in terms of instructions per packet, but they will require more processing. So the processing time has this evolution that depends on the batch size I. Then, for the rest of the talk, I introduce here the notation. So any letter in any capital letter is a random variable. Then the small letter, the A of k, is the probability. So it's the probability density function, while the capital A of k is the cumulative density function, the cumulative probability. So given that, I will show you an example of how the model works. Here, I am considering on the bottom the evolution of the queue size, so queue as a function of time. And on the top, I have the process of arrivals and the polling plus the processing. So let's imagine that at one point of time, our queue was of size I. Then when an arrival occurs, the queue will grow of I plus 1. Then imagine that processing will occur. Then now the queue will be reduced by beta, because beta is the maximum batch size. But this is not always possible, because sometimes you just empty the queue. In fact, sometimes, in this case, the j, I plus 1 minus beta, is smaller than beta, and so you just reduce up to 0. And then so on. Imagine now that we have a bunch of arrivals. At some point, we reach the queue size of L, and we have packet losses. And then so on. So this is the model that we are considering. In particular, we will use embedded Markov chains. And as shown here, the embedding times are defined to be just before the polling, the polling occurs. So the embedding times are those times where the queue size is decreased. Okay. So if we define n embedding time, we have the q of k, that is the probability of having k elements in the queue at the embedding time. And in general, this queue is considered to be at a certain batch. So the q of n is the queue size before the nth batch is picked from the queue. We can define also the x of tau a, that is the probability of having k arrivals within the inter-arrival time defined as a during the interval of time defined as tau. So in this case, this is very important because we can consider this probability of having k arrivals within the inter-arrival time defined as our arrival process during the interval time tau, that is the processing time, the batch processing required by the software router. Now, why those Q are very important? Because Q can be used to infer the state probability distribution at consequent embedding time, and we can use Q to infer elements such as the batch size and the packet loss, and I will show how. Now, here I just painted our Q. So our Q has different states from 0 to infinity. Of course, not all states will be relevant because after the state L, we have packet drop. So all states greater than L plus 1 will be a state in which packets are dropped. And now, how can we define the size of the queue after the n plus 1 batch is picked? But we can define this probability considering all the previous states. In particular, what is the probability of being in a state k? The probability of being in a state k is the probability that in the state before you were at 0 and k packets arrived, plus the probability of being in the state 1 and k minus 1 packets arrived. But you also have to take in mind that during this time, the processing is occurring. And in fact, this is why we have to take care about the processed packets. And in particular, the processed packets is the minimum between I, that is the state where I was before this batch, and beta, that is the maximum batch size. And so because of this, we need to distinguish between the two cases. The case at which k is less than L, so the queue is not in overflow, and the state at which k is L. That is, we have packet processing. So why does it change? Because in one case, we can go to a state k from any of the possible states within the queue. And in fact, here we have to take into account a sum for I that goes from 0 to L of the previous queue size times the probability of having k minus I minus the minimum between I and beta of packets arrived in the batch size, in the batch processing time. That is B of the minimum between I and beta. While in the other case, we need also to take into account all the possible combinations, so all the possible packets that are arrived from J to infinity in all the possible states that are causing the overflow of the queue. So this is very important because under stationary conditions, we just detect the Q of k, that is the limit for n that goes to infinity of this formula. So then again, why we deal with the Q sizes? Because we can easily detect what are the batch sizes, the vector sizes. In particular, the vector size is exactly the Q size when the Q is not when k is smaller than beta, but we need to take into account all the possibilities, so all the flow, all the states that are from beta to infinity when k is exactly the batch size. And again, packet loss is just defined as the expected values of the number of packets that are lost divided by the expected value of the number of arrivals. So what we did is that we simulated this model using, so first of all, we took some measurements. We took some measurements in our device using a single CPU core, using a queue size of 4,000 packets for 96, a maximum batch size of 256, and we had different rates at which we collected the measurements of the processing time. And now what we observe is that when we tune the model tuning is very strange because of possible overfitting. In fact, here I show you what happens with the mean service time when we do a per rate fitting and a global fitting. So here, if we use a per rate fitting, we change our expected values of the batches as a function of the mean service time, because we are projecting this curve with a higher slope than expected. And this is because for smaller rates, our processing time is not efficient, and so we expect that our curve is growing faster than what is real. So we just opted for a global fitting, so we do not consider at all the difference in the input rate. We just consider all the measurements took at different rates in a single fitting procedure. And we show you here that for two different process arrivals, our mean batch size is exactly what we are expecting. In fact, in this plot, I am showing our measurements in blue and the results from our model with a global fit and with a per rate fit. And notice how the fitting strategy is what affects the modeling, while the inter-arrival distribution does not. And in fact, for both distributions, for a simple Poisson distribution and for a negative binomial with 0.5, we are all able to detect precisely the mean batch size as well as the saturation regime. The saturation regime is when our software router is in overload and so is losing all packets, but is constantly at a queue size, at a vector size of the maximum allowed batch size. So what can I show you right now is that we continued our validation using different rates, different arrival processes, and we measured the Jensen-Shannon divergence as well as the relative error among our predicted distributions and the observed distributions coming from the measurements. And we see that for all the cases, the peaks are always at the correct point. Of course, here some details are lost, like this double mode that occurs in the measurement is not caught by the model. But this is anyway sufficient to allow us to have a JSD and a relative error that is really low. So in the end, we tried different process distribution, and since the Poisson is the most simple and it produces the best results, we just continued with the Poisson, with the simple Poisson distribution. So the packet loss, as I told you before, our model is able to detect the lossy regime. But how good is this detection? In the sense, what is the percentage of packets that are lost? And here I show you the results of both obtained both from the measurements and at the model. So we observe that the model is able to catch exactly the beginning of the saturation, here at 8 gigabit per second. And it is also able to detect the evolution of this lossy regime. So in particular, at 10 gigabit per second is correctly predicting that we are losing 20% of all the packets. So in the end, what are the outcomes of all this part? That we managed to predict our performance indicators with very high accuracy and with relatively simple assumptions. So I'm on time, and I can conclude this work saying a few words about NFV. So I think that NFV is a very interesting research domain, especially in this period of time, because you have to deal with many different aspects. You have to deal with the engineering aspect of networking. You have to deal with the modeling part of it. So you still have the opportunity to provide contributions in relatively different areas of the networking. Furthermore, I think that this is also useful for applying some new modeling techniques, such as machine learning. In particular, I recently received funding for a project that is called Artificial Intelligence for Performance. This is a project that I am doing in collaboration with TU Munich, and I will be working on it until the end of the academical year, so until not the academical year, the solar year, till 2019. So this is a very interesting topic for me at this moment. Now, the contributions that I showed you in this talk are just twofold. So I talked about our performance analysis on the software routers. We are targeting reproducibility of research. So our platform is actually here at Telecom ParisTech, but we plan to extend it to make it open and to let other people also to access our resources to validate their own approach, their own software routers, but also their own applications built on top of the software routers. I'm currently working on providing the explanations on why the acceleration techniques work, because we observed that batching works, but why this is working? Our measurements showed that this is due to the reduced number of instructions per clock cycle. But before, we didn't know why it was working, and it was just, yeah, it works. And finally, for the analytical part, I provided just the basis for a very simple model. I only showed you our model for a simple forwarding function. But we are also planning to extend it for more complex functions. One of these is also already in our Infocom paper. But in general, those assumptions that we have are sufficient for dealing with most of the key performance indicators. And also, a lot of this modeling part was made possible thanks to an intense data collecting campaign that we did on our device. And data collection is also another aspect that is very problematic for software routers, because when you start collecting data, you start affecting also the performance. In fact, every clock cycle that you introduce to your processing is a clock cycle less that can be used for regular packet processing. And so if you measure, if you observe at the endpoints a rate of some gigabit per second, when you start measuring in details what's happening inside your software router, you may end up with numbers that are not reflecting the exact measurement that you already took. So for all these reasons, I am currently looking for interns. I already have 2. But you see, there are many, so the topic is very diverse. But I hope to have given you a clear vision on what's going on here. Thank you very much. Yes?
So, very interesting talk, and from a different perspective from my view, because actually we face similar problems in data stream management system. Mm-hmm. And to some extent we came to similar conclusions. Mm-hmm. So, for example, we use something similar in order to do provisioning. Mm-hmm. And at the same time, doing this provisioning, it allows us to make some prediction about the load shedding. Mm-hmm. And there in the load shedding is not just blind throwing tables. You try to do it in such a way that the output of the result mm-hmm. is within a fixed bound error yes. as part of the result. So that is one feedback that mm-hmm. you might want to see. The yeah. second thing is that we have exactly the same notion of batching mm-hmm. and train scheduling. Mm-hmm. And the conclusion in our experiments was that it's similar to what you have just said, is that the cost of processing the tables in a queue mm-hmm. is fixed. Mm-hmm. What actually happens if you have a smaller queue, the amelioration of the context switch mm-hmm. that takes in order to read 3 or 20 mm-hmm. is the same cost. Yes. So if that is the reason why you have this. And now if you do the train scheduling where you have a sequence of operators in our case, mm-hmm. a sequence of routers, and you synchronize yes. them, then in that case you can minimize, in fact, the losses because you can empty the queues mm-hmm. faster. And this is what we call rate-based scheduling. Yes. You might want to see some of these things and see how these are applied in your context.
Yes.
There are so many similarities which are actually beneficial for both
mm-hmm.
the upper level and the lower
yes,
level.
Yes.
So that is my comment.
Yeah. Thank you. Just another comment on what you just said. In the high-speed domain, they typically don't want to have many bigger queues because they prefer to compress the latency rather than providing a better packet. Yes. So, in fact, our latency was bounded by 100 of microseconds, which is very good. But yes, potentially, if you can do some adaptation, like you add online additional queues where you store packets, this can, yes. So this can, of course, provide a better throughput. And we need also to find what is the correct application for that. Probably for very reliable networks where no packets should be lost, that's very interesting.
Yeah, in fact, that is interesting because we thought the same thing for real-time applications.
Mm-hmm.
The
yes.
loss of packets is very critical.
Mm-hmm.
However, whatever you do,
mm-hmm.
unfortunately, unless you do reservation,
mm-hmm.
or over-provisioning,
yes.
then you cannot do that. So that you have to come up with a little bit more intelligent
mm-hmm.
shading.
Yeah.
Or scheduling in order to achieve that. Because mm-hmm. some operators might generate results that you are not data producing rather mm-hmm. than data consuming.
Yes, yes.
And that is a non-deterministic
mm-hmm.
aspect of this computation.
Yeah.
But it's interesting. Yes.
Okay,
We
thanks.
can talk more afterwards, actually. It's
Sure.
very interesting
Thanks.
to learn about these things.
Thanks. Yes.
We've already talked about this together, but I wanted to say it publicly to get clearer in my mind. You're showing that batching works only at high load. At least you only get reasonable sized batches when you get a load getting 80% or more. And yet, in the last slide, you showed that the loss rate when you get a load of about 80% is 5% or more and going very much higher.
Yes.
So what's a typical load you think would be sustainable? Surely 5% loss is very high for TCP flows or whatever. I mean,
yes, and in fact, so the load that can be sustained is mostly application dependent. So it and not only this, but it also depends on the type of the software router that you are utilizing. In particular, here I am only showing one experiment on a single software router, but tomorrow we have a meeting, and so Tianzu can also show you that for other software routers allow even at 10 gigabit per second 0% of packet losses. So then, to your question, I think that this all goes to that to the slide that I am showing you here. So I think that one solution could be to try to take this part here that is very close to the overload and push it as much as possible to the edge. So we were working on some sleeping mechanism so that they can sleep, they can do micro sleeps in order to wait for more packets to arrive at the line card, and so to go directly to the high speed mode. And so introducing 5 microseconds of artificial latency, but to push the device to the maximum part will be desirable. And in particular, we can try, for instance, to work at 8.5 gigabit per second with 0 packet losses. If we in fact, it's 8.2 here, and we try to maximize the size of the batches. But the load that is sustainable really depends on the software router.
But the model is independent of the particular implementation.
The model is
gave that result, the batch size.
Yes, the model is independent, but the model is trained with the measurements collected here. In particular, the batch size processing. So the processing time required to perform one batch is not provided by the model. It's provided by our measurements and fitted with a linear fit. So that's why the model is yes. Yes.
Leonardo, just a question about the size of the queue, and here you were showing the size of the queue of the NIC. While if I understood well, you have like a software queue where you did all this modeling. So a question about the software, the size of the software queue. How do you define it? Like, what's the ratio between its size and the size of the real NIC? So if you were talking about the packet loss, you were talking about the packet loss in the...
Yes, so the size of the software queue is this, the software ring. The hardware queue is this, defined at the hardware. You typically want the ring to match exactly the size of the NIC. So in particular, our case was 4,000 packets, but you can use even smaller queues. At the end, when you are in a lossy regime, you will lose those packets anyway. So buffering more will not introduce more higher performances. So yes, the packet ring is typically one-to-one matched with the hardware queue.
So the question is that what makes the queue overflow is the processing and not the...
Yes.
Okay.
Yes. Yes.
I would like to ask you something related to your plan for your future work.
Yes.
What I don't get is the following. what is the need of empirical models for machine learning data? Given that you have very precise and close, let's say, models, domain models about the phenomena that you want to study. Usually we use the empirical models when such kind of domain-specific, let's say, analytical models are difficult to obtain or they frequently change in time.
Yes.
So what is the intuition? If I'm not violating
No.
potential rules?
No, not at all. And the intuition is here in this plot in particular. What matters is that for this particular talk, I only talked about a single software router and the evaluation and modeling of that device. But in my vision, software routers are NFV enables. So what happens is that the software router is typically one component in a chain of functions. So imagine that you have some end-to-end TCP connections going through your NFV network. So what you want is that we want to understand if getting some measurements having some models inside the software router will help us to infer some variables related to the TCP throughput of the end-to-end flows. So it's not because we want to model a single software router. We want to put our software router in the context of an NFV network, and we want to try to verify if we can predict, for instance, the TCP flows. The TCP flow throughput. I'm talking about the TCP flow throughput because one of the people I'm collaborating with has recently published a paper that is called DeepCom-Net, and it applies deep learning to detect TCP end-to-end throughput just using the topology of a network as feature. So it completely ignores all the details about the underlying implementation of the network. It just collects, if I'm not wrong, so there is this approach is called gated graph neural networks. So you translate the topology to an equivalent neural network, and you utilize some additional parameters such as the round trip time, which is averaged, so you don't need a lot of details on it. But only using these features can help us to infer the TCP throughput.
You know what's the problem with deep learning? You need a lot of training data.
Yes.
So the question, let's say my experience here in the lab is that obtaining such data from the real networks under real conditions is very costly, okay, even sometimes very infeasible to do.
And in fact, this is one of the challenges that I targeted, explicitly targeted for the project to get accepted. So I hope that I will solve this problem also for you. Okay. So thanks.